This is MEI Statistics Minor, Discrete Random Variables 1, Mean and Expectation. 1.4, Expectation and Variance of A plus B x. We suppose that x is a random variable. We are interested in what the expectation of ax plus b is going to be, where a and b are both constants. In other words, they're independent of our random variable x. So if we consider the expected value of ax plus b, well, we know that to be the sum of all the values of ax plus b times the probability that our random variable x is going to be equal to that value of x. Now, I can multiply that out to make ax times the probability that x equals x plus b times the probability that x equals x. And if I'm summing up two things inside a summation, I can then split those apart to get the sum of ax times the probability that x equals x plus the sum of b times the probability that x equals x. Now, as I said, a and b are constants, so they are independent of the values of x. So I can take them outside my summations to get a times the sum of x times the probability that x equals x plus b times the sum of the probability that x equals x. Now we should recognise this. Sum of x times the probability that x equals x, that is simply the expected value of x. So it's going to be a times the expected value of x plus b times, well, what is the sum of all the probabilities? We've already established that that must be equal to 1. So that's simply going to be plus b times 1, which of course is equal to b. So I can use that result in this example. So if I let x be the score on a fair six-sided die, and I let y be a new score that I get by doubling and adding on 5 to that score, I want to find the expected value of y. So first of all, we find the expected value of x, which using the formula from last time, we know to be a half times n plus 1. Value of n in this case is 6. And so that is 7 over 2, or 3.5. Now our expected value of y is found by realising that y is equal to 2x plus 5. That's how we double it and add on 5. So using this formula up at the top, I can write that that is equal to 2 times the expected value of x plus 5. So that is 2 times 7 over 2 plus 5, which of course is 7 plus 5, which is 12. So we can do exactly the same thing with the variance. It's just a little bit more complicated. So the variance of ax plus b is the expected value of ax plus b squared minus the expected value of ax plus b all squared. Put that into sigma notation. That is going to be the sum of the ax plus b squareds times the probability that x equals x minus what we already know to be the case, which is a times the expected value of x plus b squared. I can now multiply out the bracket in this first term, and I can take out the constants from outside to outside the bracket. So I'm going to get a squared times the sum of x squared times the probability that x equals x plus 2ab times the sum of x times the probability that x equals x plus b squared times the sum of the probability that x equals x minus a squared times the expected value of x squared minus 2ab times the expected minus b squared. Now that's quite a long line, but you'll soon notice that things start to collect together because we've got two terms with an a squared in them that very neatly go together. So we'll have a squared times the sum of the x squared times the probability that x is x minus the expected value of x squared. We've got two terms with a 2ab in them. So that's going to be a plus 2ab times the sum x times the probability that x equals minus the expected value of x. And then we have two terms with a b squared in. So it's b squared times the sum, the probability that x equals x, minus 1. Now we should recognise what is in there, because that is simply a squared times the variance of x. We should recognise what is in here, because that is the expected value of x. So then if we subtract the expected value of x, our 2ab term is simply going to be multiplied by 0. Similarly, the sum of all the probabilities we know to be 1. So if we then take away 1, that means our b squared is going to be multiplied by 0 as well. So in summation, it's simply going to be a squared times the variance of x. Now, is it surprising that we have a squared instead of a? Well, no, not really. If we think about it, variance is always a squared measure, isn't it? So we would expect the scaling factor to be squared also. Note that the standard deviation sigma is not going to be a squared measure. It is going to be scaled in a linear way. Is it surprising that there's no b? Well, again, not really, because if we have two distributions that differ by b, so if I get from this one to this one by adding b, the spread isn't going to change, and we remember that variance and standard deviation are both measures of spread, so adding b and just shifting it across is not going to have any effect on the variance. So, for the die example, if we have y equals 2x plus 5, then the variance of y is going to be equal to 2 squared times the variance of x. So that is going to be 4 times 1/12 6 squared minus 1, using the formula that we established earlier, and that is going to be equal to 35 over 3. In the final video of this series, we're going to be looking at linear combinations of random variables.